Hi, my name is Vasily Bunakov, and I'm one of the developers of the LightAutoML framework. In the previous materials, we got acquainted with the basic functionality of LightAutoML. But we are constantly developing the library. Therefore, I recommend following the updates on the repository on GitHub and on our Telegram channel. In this video, I will talk about the additional functionality of the framework developed recently. We will consider new types of modality problems and find out what new algorithms are now available in LAMA. We have expanded the functionality of LAMA with multi-label and multi-output tasks. Now they have full support inside the preset, including new pipeline models and modified target encoders, as well as their own metrics and losses. In addition, we have expanded support for input data types for solving machine learning tasks. Recently, new modalities have been added to LAMA. One of them is linked tables, which is direct support for database structures. This functionality uses common approaches based on the Feature Tools library and allows you to automatically generate and select features directly from related tables. For example, you will be able to work simultaneously with transaction history, customer attributes, and order attributes. The example of usage you can find in the corresponding tutorial on GitHub. Another fundamentally new direction in LAMA is time series prediction. Let's take a closer look at the features of LAMA for time series. The diagram shows the add-on structure for working with time series. Here is multi-output regression task, in which k forward points are predicted at once. Our data is stored in a long table with a time series and additional features. The table remains unchanged during model training, and this avoids unnecessary copying of data. The reader sets the logic of series preprocessing and allows us to avoid looking into the future during the training. The dataset structure stores the original series. Features based on the available history are generated in the ML pipeline. Also, we have several strategies how to work with the trend in the initial series. For predicting several points ahead, we use only models with multiple outputs. This avoids problems with long-term autoregressive prediction, as in the case with other solutions. In terms of convenience, we store series ID and date for each observation as additional meta-information. Now, let's talk about what kind of time series you can predict. LAMA time series was designed to work with regular series in which observations are equally distant from each other, with a few non-random omissions. For example, it may be weekends. The series can be one-dimensional, with or without a trend. Also, the series can be multidimensional, homogeneous without a trend. At the same time, the series should not be too short, namely at least 100 observations. To understand whether the LAMA is suitable for your specific task, you can use the following checklist. Firstly, you predict several points ahead, optimally up to 30. Secondly, the history window for feature generation is fixed. Actually, its size depends on the number of desired log variables. Also, for one-dimensional series, you can have a linear trend and additive seasonality. OK, this concludes the discussion of LAMA time series. Our next topic is the new machine learning algorithms recently added to LAMA. The following algorithms are now available in the Tabular Preset. Firstly, it's sklearn implementation of random forest working with multidimensional output. Secondly, there is a large neural networks model with several classical architectures available and a couple of techniques to improve quality and convergence, such as averaging weights from specific epochs, initializing the last layer with a target, selection of network topology by cross-validation, transfer of an arbitrary custom architecture, and this is not a complete list. Another algorithm recently added to LAMA is PyBoost. PyBoost is an original toolkit from the developers of LightAutoML with a new gradient boosting algorithm. Let's take a look at PyBoost in more detail. Consider the case when you have 200 to 300 products, and you need to choose among them 4 to 7 offers that are the most suitable offers for the client. In this case, it's most efficient to use multi-label problem statement, also called a non-rigid classification. However, only a few models support such tasks, and in most cases they have linear complexity depending on the number of targets or classes in the multi-class classification problem. Ultimately, this leads to extremely poor performance with a large number of classes. To address this issue, our team is working on improving gradient boosting. For example, we have developed the sketch boost algorithm. An article about our development was published at the New IPS 2022 conference. The algorithm is already implemented in our PyBoost library, and LightAutoML supports calling algorithms from it. There are several advantages of PyBoost. Firstly, this framework is open source. Secondly, it calculates faster and with less memory consumption compared to other tree-based approaches, which, by the way, doesn't prevent it from showing better results. Currently, this is the only algorithm that fully supports multi-label tasks without the explicit limitations that CatBoost has. And now, let's consider two versions of LAMA designed for a special computing infrastructure in the case when you need high-performance computing. Spark LAMA is a distributed version of LAMA. Now it works under Spark 3.2 and higher. Working with Spark LAMA is virtually the same as launching a regular LAMA Tabular Preset. The library is written in PySpark, partly in Scalar for maximum acceleration. Let's take a look at the implementation features. We tried to speed up the pipeline as much as possible, so we avoided using join operations where they are not really needed. Also, we cache everything and use checkpoints only where necessary, for example, at the beginning of the whole pipeline while creating a bucketed dataset, or at the end of the first-level pipelines. Nevertheless, we tried to give control over checkpointing to the user, so we introduced an additional entity that determines when and how checkpoints will occur. We also wrote a customized string indexer in Scalar. Using this tool, we perform feature preprocessing and create an AutoML transformer, which supports saving, loading from disk, and further application on real data. All of the above innovations help machine learning algorithms work efficiently with millions and billions of rows in a distributed infrastructure. And what is important, the more data we have, the greater the acceleration of calculations increasing the number of nodes. In fact, it grows up to a linear trend. So, when we have 16 executors running, the usual LAMA on 100 million rows dataset accelerates by almost 10 times using SLAMA. Another special version of LAMA is LightAutoML GPU. This is an end-to-end pipeline using GPU in tabular and natural language processing presets. We use the NVIDIA Rapid library as our main backend, and we also use the DeskCuda library for distributed computing. So, we can do now GPU calculations for each stage of the pipeline from processing to blending. To work on several GPUs, we use a number of approaches. Firstly, we use the built-in functionality of dependent libraries, for example, the data parallel in PyTorch library. Secondly, we have developed special tools for parallelizing independent parts of the pipeline. One example is hybrid data preprocessing, where pandas data frame turns into CUDF or DeskCUDF data frame while transferring to multiple GPUs at the same time. Another tool is parallel training of models. We can parallelize calculations for both data and faults as shown in the diagram. It gives us a significant acceleration for medium and large-sized datasets. 2 to 3 times on preprocessing stage and 5 to 10 times on learning stage. For example, in the classical fashion MNIST problem, the GPU version of LightAutoML increases the speed by about 6 times when compared to the basic version. Whereas, using 2 GPUs simultaneously, you can increase the speed by more than 9 times. The PyBoost algorithms mentioned above have also been added to LightAutoML GPU.